All right, let's begin by talking about the reflection of light. Light itself comes from a source of some sort. That source could be something like the sun, or it could be like a light bulb or some other source. The simplest type of source is called a point source. And a point source you can think of as truly a point in space, and then light rays are coming outwards in all directions from that point source. Okay, that point source then, if I imagine some rays coming out at an angle like that, then there are going to be wave fronts associated with that. So what a wave front is imagine that you've got light that starts from the point source, spreads out in all directions, and then all of that light that's in that circle right there, in that concentric sphere, left the source at the same instant of time and is spread out to that point over time. And of course that sphere right there is going to grow in time, and out here would represent another time. So it's growing as the light waves spread out. So that represents then a wave front. If I had one little area here, let's say that represents all of the one small section of this area here, then that represents a portion of a wave front. And that area is going to increase as the square of the distance. So if I go out here twice as far, then this area here becomes 4 times larger because of the distance here. So this area, if it's twice as far away, is going to be 4 times larger. So the area increases as the distance squared, which is why the intensity also decreases as 1 over the distance squared, because the same energy that came from the source is now moving outward and is spread over 4 times larger area. Now, if you're very, very far away from a point source, these spherical wave fronts are close to plane waves. You know, just think about these spheres growing and growing and growing until the edge of it, if you looked at the edge, you wouldn't notice any curvature at all. So that would represent then something like a plane wave. And a plane wave, the rays coming from that would all be parallel. Okay. So you have plane wave fronts. In that case, you have rays of light that are radial parallel lines that are perpendicular to the wavefront. The sun's rays are far enough away that we think of them as coming in parallel. So if this represents, say, the ground, then here comes the sun's rays coming in like that, and then another ray would come in parallel to that. And we assume that that's the case for the sun, even though the sun is not an infinite distance away, and it's certainly not a point source. But those rays come in and they reflect off of a surface. Now, reflection is the topic here. And most people, when we think of reflection, they think of something like a mirror. However, everything reflects light. I mean, everything that you can see reflects light. In fact, that's the way that you're able to see. Light comes from a source, let's say from the sun, reflects off of any surface, like, look around you at the walls, at your hands, at any object in the area. And the only reason you're able to see that is because light comes from some source, reflects off of that surface, and then enters into your eye over here, and you're able to see whatever it is you're looking at. So it looks like you're looking along that ray of light to whatever this object is back here, but the truth is the light has to come in, illuminate that object, and then some of that light then goes into your detectors that you carry on your skull called your eyeballs. And we think of these as smooth surfaces, and if they are smooth surfaces, then we will get nice reflections that are where the rays are parallel. However, you could have a rough surface, something like that, and then when the rays come in, they may come in parallel, but they don't necessarily reflect parallel. So a ray may reflect this way, This ray may reflect that way. Another ray may come in and reflect a completely different direction. So if you have multiple rays coming in, then you get scattering of light. That's why a person over here can look and see this object. A person over here can also look along this ray and see that object. A person over here can look along that ray and see the object. So light hitting a surface that is not perfectly smooth, then the light rays are going to scatter in all sorts of directions. Okay, well, the idea of reflection is that, but the rule or the physics of reflection is very, very simple. We have something called the law of reflection. The law of reflection is very simple. So here, let's say we have a reflective surface here, and we have a ray of light that comes in from that angle right there and reflects off in that direction there. Well, the law of reflection is this. You measure angles of incidence. This would be the incident ray, and this would be the reflected ray. You measure the angle of these two rays relative to the normal to the surface. So that line represents a dashed line there represents an angle that is 90 degrees from the reflective surface here. So this would be the angle of incidence. Let's call that theta I. And this would be the angle of reflection. Let's call that theta R. Then the physics of this is really straightforward, because the angle of incidence is equal to the angle of reflection. And that's pretty much all there is to the law of reflection. Everything else that comes about because of that is just a supplement or a detail regarding the law of reflection. So let's say that we have something like a mirror that is standing vertically here, and it is vertical to the ground. So this represents the ground, and there's a person on this side over here. Let's draw in that person as a stick figure. And there. And the person's eye level is right there. All right, now this person can see themselves in the mirror. But if you'll think about this, the light from whatever sources happen to be in the room are striking this person and then scattering off into space around the person. So one ray of light that, let's say, is striking the foot right there is going to come in and hit the mirror and then reflect off. So I'm drawing arrows to indicate the direction in which the light is moving, and then reflect off and go into the person's eyes. So that person then looks along that ray and sees the reflection of their foot there. Now, the angle of incidence in this case is that angle there, and the angle of reflection is that angle there. And those two angles are going to be the same. All right, now if the person looks at their head, let's say the top of their head at that point right there, then the light ray comes in, strikes the mirror. I'm sorry, it's a reflected light ray in the first place, but it's scattering off of the person, so that light ray is coming, striking the mirror, and then reflecting backwards in that direction into the person's eye, so the person sees the top of their head. So this distance right here from there to there, within that, the person is able to see their entire body then. All right, but think about what the person here is seeing when they look at this. They're looking along this reflected ray, and that reflected ray, if we continued it on out, would end up over here. So the person's foot, which was here, appears to be back here at that point. And the person's head, if you go backwards along this ray right here, appears to be back here. And that represents then the top of the person's head, let's say right here. So what they would see then is they would see themselves in the mirror, something like that. And if I had been careful to draw these angles and all of this stuff very carefully, like with a straight edge and a ruler, and measure my distances very carefully, here's what you would discover. The distance from here to the mirror is the same as the distance from here to the reflection. Now, this one back here is not a real distance, it's just the distance that it appears to the person on the other side of the mirror. So the person on this side of the mirror, this is the real person. So this person would be considered the object of the reflection. And this person would be considered the image of the reflection. And the image would appear behind the mirror the same distance that the object is in front of the mirror. The fact that this person is behind the mirror, or appears to be behind the mirror, makes this image virtual. And the person that is in front of the mirror, a real. So we have a real object and a virtual image for this plane mirror that we've got drawn here. And like I said, if this distance here is x, then this distance here is also x, but behind the mirror, so we could say that that's negative x. Then this would be the 0 point right there. Now there are a few things about this reflection in a plane mirror that you need to notice. First of all, notice there is only one image here. Okay? The person is not seeing multiple images, there's only one image. If there happened to be another person, let's draw another person back here, if they happen to look at this person's image, they would see exactly the same image. They're not seeing another image, there's only one image back here, and this person can see it, and if this person is positioned properly so that they can see in the mirror, then they would see that same image as well. They would not see another image. Another thing about this is the image is upright. Now you might think, well, of course it's upright. That's the way these mirrors work, but that's not always the case. And you'll see that later on when we start talking about curved mirrors, that the image is not always upright, but in this case it is. The image is also the same size. In other words, the image appears to be the same height and the same width as this person over here. So the image is the same size as the object in this case. What we would say is that it has a magnification of 1. So there's only, if you were to take the size of this person's head here, multiply it by 1, you get the size of this person's head over here. So that's what is meant by magnification. It has a magnification of 1, meaning that the object and image are the same size. And we've already said this, but the image appears as far behind the mirror as the object is in front of the mirror. So we'll say the image, I'm going to run out of room there, I'm going to write it down here. Okay, so those are the prominent things that you need to notice here when you're talking about a reflection in a plane mirror. Now, when we start talking about curved mirrors, the type of mirrors that we're specifically going to talk about are considered spherical mirrors. So here's the basic idea of a spherical mirror. Start with a sphere. Now I'm going to attempt to draw a sphere here. I will probably fail, but that's the approximate sphere. Now, take a portion of that, and that curvature right there represents the type of mirror that we're going to talk about. So there's a piece of glass right there that has a reflective surface on it. Now the reflective surface can either be on the left side or the right side. If the reflective surface is on the left side here, then you would stand over here on this side and you would look into the mirror and possibly see a reflection. Okay, if it's that shape, then that's called concave. So a person on this side sees that as a concave mirror. However, if the reflective surface were on the opposite side, on the outside here, then this person would see a Now, it's not both concave and convex, because the reflective surface is usually only on one side. It would be weird to have a reflective surface on both sides. But if you're viewing the reflective surface from the concave side, it would be on the left side. If you're viewing it and it has a reflective surface on the right side here, then that's a convex mirror. Okay, now each of these, whether concave or convex, has a radius associated with it. And that radius would be this radius right here, the radius of curvature. And it doesn't matter if it's concave or convex, you have a radius of curvature associated with spherical mirrors. Now, if you were to take a spherical mirror and do something like this, let's say we've got a concave spherical mirror. So this is concave, meaning that the reflective surface is on this side. So that represents the reflective surface. Now, there is a radius of curvature associated with that. Let's put that right there. That would be what's called I'm going to call that the center of curvature. The radius is actually the distance from the center to the mirror, so that's the center of curvature there. If you were to take light rays that travel along this path from the center to the mirror like that, I'm just drawing that as an axis. But if you were to take rays of light that come in parallel to that axis, when they strike the mirror, here's what you would discover. They reflect off. Remember, angle of incidence equals angle of reflection, but you've got this curved surface here now. They would reflect off along a path that looks something like that. Okay, if you did the same thing then with another ray, let's say we take another ray on the other side here, and it comes in and it's parallel with the axis as well, so it's traveling in that direction. Then when it reflects off, it goes something like this. Like that. And you would discover that those rays, regardless of where they're at here, let's draw another one. Let's say another one comes in here, in that direction, and then it reflects off. When it reflects off, it also goes through that point where all of these rays are crossing. And regardless of where you draw that ray coming in, they reflect off through that point right there. So that point is called the focal point. The focal point is usually symbolized with the letter, capital letter F. So sometimes you'll see a mirror being drawn here like that. Here's the central axis, and a point will be marked as F. And then another point out here will be marked as C. That represents the center of curvature. That represents the focal point. Okay, now the distance from the center of curvature to the mirror, well, that's the radius of curvature. The distance from the focal point to the mirror, well, that's called the focal length. So the focal length would be this distance right here. Okay, that's the focal length. And for a spherical mirror, this is the case. The focal length, which we'll symbolize as small f, is equal to 1/2 the radius of curvature. Now that is true only for a spherical mirror. So the focal length of this concave mirror here would be half of whatever the radius of curvature is. That would be for concave. If I had done this for convex, let's draw that case. Remember, for convex, let's draw the mirror shape like this, and we'll say we'll have reflective rays. First of all, let's sketch in the axis. So that's the axis that goes right to the center, so the center of curvature may be over here somewhere. There's still a radius of curvature associated with this, but the reflective surface now is on this side. And now when a parallel ray comes in here, it strikes, and when it reflects off, well, it goes out in this direction. Okay, let's draw another one on the other side. When it comes in, angle of incidence equals angle of reflection. It's going to reflect off and go out in this direction then. Okay, you might say, well, those rays don't converge like they did in the case of the concave. You notice the reflected rays converge to a point, to the focal point. Well, here, the rays are not going to converge. If I drew another one out here, it reflects off and it goes out in this direction. So the rays are definitely not going to converge here, unless you think about what's going on the other side of the mirror here. If you were to trace these lines back, they do intersect at a point. And I didn't draw this one carefully. I'm going to draw it like that. Ignore that ray there. They do intersect at a point. and that point is the focal point. So the reflected rays, if you trace them back, then they do converge at the focal point. And in this case, the focal length, since we're talking about a convex mirror, the focal length is said to be minus 1/2 of the radius of curvature for a convex. So the negative sign indicates that it's behind the mirror here. The focal length is behind the mirror. Now you can use a technique called ray tracing to determine the locations of images given a specific object. So I'm going to try to do that right here. Now I grabbed myself a straight edge so that this is just a little easier. If you have to do this on an exam, which you might, in fact I guarantee you will, you'll want to use a straight edge for this. So let's start this way. Let's draw what we call the axis here. And then let's draw a, let's start with concave, and we'll draw that something like that. Okay, just concave. Now, let's say the center of curvature is right here, and then the focal length, focal point is going to be half of that distance there. And we're just estimating here. I didn't measure things, but you might want to. Okay, now, to place an image, you need to know where your object is. So an object, let's say the object is out here at this point out here. Let's just draw an object out here. And to be honest, the best type of object to draw is just a straight line, a stick. But you need to know which end is up, so you put an arrow on the end of it. So this represents the object, capital O. All right, now in order to do this technique called ray tracing, we should be able to locate the image somewhere along this axis based upon using the technique of ray tracing. To place the image, you need to draw rays coming from the object. So remember, light from whatever source is out there is striking this object and then scattering off into space. Well, we're specifically going to look at rays that come off of the object, travel and hit the mirror, and then reflect off somewhere, and where they converge is going to be the place where you locate the image. All right, now there's some rules here you need to follow. The first rule is this. A parallel ray, meaning a ray that is parallel to the axis, is going to reflect off through the focal point. You saw that in this drawing back here. If I have a parallel ray coming in, a ray that is parallel to the axis here, when they reflect off, they pass through the focal point. Now that doesn't mean the image is going to be at the focal point. It just means that rays that come parallel to the axis are going to pass through the focal point. So let's draw a ray coming from the source, coming from the object. And when it comes from the object, it goes in and it strikes the mirror at that point. Now always put arrows on your rays so you know what direction the light is traveling. And then when it reflects off through the focal point. So I'm going to try to draw this ray coming off of the reflection point and now passing through the focal point. And that ray goes off in whatever direction it wants to here after it goes through the focal point. It just continues on through. All right, so that's one ray that you know where it's going to happen, where it's going to reflect. The rays that come in parallel reflect through the focal point. All right, now we need to at least one more ray. So let's talk about the ray that comes through the focal point. Now, if you'll think about this case here, just imagine that we reverse the direction of this. Let's say that we started with this ray right here and we went in that direction. Well, if that ray passes through the focal point, then when it reflects off, it's going to be parallel. So this idea is just the opposite of the one we just drew. What we're going to do now is talk about a ray coming through the focal point is going to reflect off parallel. Previously, the last ray we drew was we had parallel ray coming in, reflects off and goes through the focal point. So it's kind of the opposite. But here's the way to draw it. Start at the same point, exactly the same point, and then have your ray go through the focal point and strike the mirror. So here comes the ray from the arrow through the focal point, and it strikes the mirror. So that's the direction of the ray right there. Now when it comes off, it's going to be parallel with the axis. So it comes off and it goes like that. So this is the direction of that ray. Now you'll notice the two rays converge at that point right there. So at that point right there, the image is formed, but what part of the image? Well, the part where the light originated. So the tip of the arrow is going to be right there. Now, the bottom of the arrow is going to be down here on the axis. Now, how do I know that? Because of the third ray. So far we know about rays that come parallel, reflect through the focal point, or rays that go through the focal point, reflect parallel. Well, there's one more. A ray that passes through the center of curvature. Remember, that's the center of this large curvature here. A ray that comes off of the bottom, goes through the center of curvature, strikes the mirror, will reflect back along the center of curvature. So a ray from the bottom goes in that direction and comes out that direction. So what does that mean? That means the bottom is going to be somewhere along the axis here. And that point where it's going to be is right here, because that's where the tip of the arrow is down here. So if I draw in the image, it's going to look like this. There. Now you'll notice it's upside down, first of all, but it's also shrunk down. The magnification is going to be less than 1 here. All right, so here's what you need to recognize from this. First of all, that would be the image right there. So we'll indicate the image with a capital I, we'll indicate the object with a capital O there. And if the object is out here beyond the center of curvature, if O is greater than C, I shouldn't say C, I should say R, because that's the radius of curvature. C is a point, R is a distance. If object, this would be the object's distance measured from the mirror, if the object's distance is greater than the radius of curvature, then we have this situation that we've got drawn right here. First of all, the image is real, meaning that it's on the reflected side, doesn't appear behind the mirror, it appears in front of the mirror. It is reduced. That means that it has a magnification, which I'll symbolize as little m, that's going to be less than 1. And it is inverted. And those three things would hold for the image regardless of where you put your object out here, as long as the object is past the center of curvature here, past the radius of curvature. And so that's true for an object past the center and to the left of the center. Okay, but what if you located the object, let's say, between the center and the focal point? Well, if you did that, you could draw rays once again. But I think you can probably imagine what's going to happen here. If I located an object somewhere between C and F, then the image is going to appear out here. Because you could exchange these two things. Let's change this O to an I and this I to an O. In other words, we're just changing places with the image and object if we do this. And what you'll see is that if I were to put my object right here, then draw the parallel lines. So a parallel line comes into the mirror, reflects off, and goes back here. A line that goes through the focal point hits and reflects off parallel. So those two lines would converge back here to make that image. Well, let's go ahead and do that and just show it happening. We'll redraw this whole thing. We'll start, draw a line to represent the axis here, draw a curved concave mirror. We'll estimate that right here is the center and right here is the focal point. And we're going to locate an object now right here. So there's our object. Okay, let's follow those rules about ray tracing so that we can figure out where the image is going to be. Well, the lines work this way. Parallel line. A parallel line that comes in and strikes the mirror will reflect off through that focal point. So I'll try to draw that now. Something like that. So the rays coming from the tip of the arrow here, striking the mirror, and then passing through the focal point. Okay. I should probably extend this on a little bit farther because I happen to know where this thing's going to end up. So we'll just extend it on. Okay, now the next one would be a ray passing through the focal point reflects off parallel. So let's do that one. A ray through the focal point strikes the mirror there. And then when it comes off parallel. And that looks close to parallel there. So that's the direction of the ray. Now, where do those lines converge? They converge at that point right there, so that's where the tip of the arrow is going to be. The bottom of the arrow is going to be along the axis because a ray that looks like it's coming from the center here is going to strike and reflect back along the center. That would be where the bottom is. So right here. There. That's where the image is. Now, if the object is between C and F, then the image is real because it's on the reflected side. It's over here. It's not behind the mirror. It is enlarged, meaning what? That it has a magnification greater than 1. And it is inverted. Now, inverted means that it's inverted relative to the object. If the object had been on the other side here, if I had drawn this object upside down, then the image would have been right side up. So inverted just means it's inverted from what the object was. The image is inverted from the object. Okay, so we've got kind of two cases here. First of all, when the object is beyond the center, then the image is going to be real, reduced, and inverted. But when the object is between C and F, then the image is going to be real and enlarged and inverted. Okay? And that's going to be the case no matter where you are between C and F. As long as you're somewhere in this region here, these characteristics will always be the case. So you can probably see there's one more case here where we could locate the object inside of the focal point, so at a distance from the mirror that's shorter than the focal length. Okay, let's do that and do some ray tracing and figure out then where is that image going to be. So once again, I will draw an axis here. I will draw a curvature, and I will estimate where the center is. Center of curvature is there. Focal length, focal point right there. And now we're going to locate our object right here. Okay, let's use the same rules, but we've got to be careful here because the rules do apply exactly the same way that we talked about, the rules of ray tracing. However, in this case, you're going to discover that the image is going to be on the back side of the mirror. We're going to have a virtual image. All right, but let's go ahead and get started. First of all, a ray that comes parallel to the mirror. So it's coming in parallel. Now, when that ray strikes the mirror, it reflects off through the focal point. So let's draw that. There it comes, passes through the focal point. So that's the direction right there. So we've got one ray. Now let's draw in another one. Now, for here, a ray that passes through the focal point is just going to keep going. It's not going to do anything. So we want that ray to strike the mirror. But here's the way to interpret the rule. If it looks like the ray has passed through the focal point, in other words, we want the ray that's coming off of the arrow striking the mirror there. It looks as if it originated and passed through the focal point. Okay? That ray then is going to reflect off parallel. So there. All right, now you'll notice something here. These rays do not converge. They do not converge on the real side of the mirror. But if you trace backwards, let's trace it backwards, and let's draw these lines as kind of dash lines here. And the rays that I'm tracing backwards are the reflected rays. I'm not tracing the incident rays backwards, I'm tracing the reflected rays backward. And you'll notice they converge over here at this point. So that represents the point then where the image is formed. All right. So in this case, we have a virtual image. If the object is less than the focal length, in other words, if it's inside the focal point, in that case, the image is virtual. That means that if you were the object here and you look over here, you're going to see something that is on the opposite side of the mirror. That's the way that most of us think of, mirrors working, bathroom mirror anyway, working like that. It creates a virtual image. It's also enlarged. So what does that mean? That means magnification is going to be greater than 1. And unlike the other two, this is upright. An example of this kind of mirror would be something like a makeup mirror. A makeup mirror is one that has a curvature to it, and when you look at yourself in the makeup mirror, you see an enlarged image that appears on the opposite side. So you're looking, holding the mirror up, sticking your face up close to the mirror so that you can see. Then what happens is you have an enlarged image, which is what you want in a makeup mirror, because then you can see the details so that you can fill in all the cracks and spackle all of that. That's an example of this type of mirror. Would be a makeup mirror, but your object is located inside the focal point of the mirror in order to create this enlarged upright image. Okay, now let's think of these special cases. For example, we've talked about things that are beyond C, having objects beyond C, having objects between C and F, and objects inside of F here. But what if the object, let's say the object is at infinity. Well, if it's at infinity, if the object is way out here off the left side of the paper, long ways away, then the rays are going to come in parallel. And when the rays come in parallel, they're going to converge at the focal point. So in that case, you would have an image that forms right at the focal point. So if the object is at infinity, then what we have is we have an image at the focal point. Okay, so all of the light from the image would be concentrated at that one point. There would be no upright or enlarged or so forth, because it would just be an image at a point. Now, that might be useful if you're looking at stars, for example. Light from a star comes in, and if your job is just to measure the brightness of the star, then it would be useful to have all of that light concentrated at a point, and that point would be where your detector is. So this is that would be useful. You would then build a concave mirror that acts like a telescope. Okay, well, what if the object, that says I, that should say if, O is at infinity. But what if the object is at C? In other words, the object is right there at C. Well, in that case, that's one that we could probably draw. I'll just do a real quick sketch here, because I think you can imagine what's going to happen here. If this is at C, and that point right there is F, and we locate our object right here at C, then it comes in, reflects off down here, comes in, reflects off down here. What happens is the image is also going to be at C. So if the object is at C, then the image is also at C, and it's inverted. And the magnification is equal to 1. So in other words, the object and image are the same size at that case. Okay, now here's the other special case. What if the object happens to be at the focal point? Well, that's sort of just the opposite case of this. If the object happens to be at the focal point, then the rays are going to be reflected to infinity. So all the rays are going to come off parallel. So if the object is at the focal point, then the image is at infinity. All right, so that takes care of all of the possible locations for the object to be for a concave mirror. Between the mirror in F, at F, between F and C, at C, and then greater than C. You should be able to use ray tracing then to locate the image given that sort of circumstance. Okay, now let's do ray tracing for a convex mirror. So once again, I'm going to draw the axis here. I'm going to draw convex. Let's do it this way. This time the reflective surface is on this side. Now there is still a center of curvature. Let's put it right here, C. And then halfway between is the focal point. All right, now in this case, the object has to be on the reflective side of the mirror. So the object has to be over here somewhere on the left-hand side. So it doesn't matter where we locate it, we're going to end up with the same result. So let's put our object right here. And let's go through the ray tracing rules once again. But let's do it this way. You have to interpret the rules properly. A ray that comes in parallel and strikes the reflective surface is going to reflect off and pass through the focal point. But you'll notice in this case, it's not going to go through this. This is on the other side of the mirror. So what happens is it reflects off as if it came from the focal point. So that's the reflected ray there. If you were to trace it backwards, let's go ahead and do that. If you were to trace it backwards, it would look as if it originated from the focal point. Okay, so that's the first ray. The next ray is going to be a ray that passes through the focal point is going to reflect off parallel. So let's draw that one. A ray that's heading towards the focal point here. So the ray is heading towards the focal point, but obviously the mirror got in the way. It couldn't get to the focal point. But when it reflects off, it's going to reflect off parallel. So something like that. Now, once again, trace the reflected ray backwards. And right there, that's where the image is going to be. And that's going to be true no matter where you locate your object out here. If we would have put the object up real close, it would have been the same sort of thing. This ray, the one that's coming parallel, that ray right there, if I were to move my object in closer, as long as the object is the same object and has the same height to it, this reflected ray is always going to be the same. So this ray is always going to be the same because this ray is always going to be the same. So what does that mean? That means the image back here is always going to be along this line. So if I got closer, I might have an image like that, or like that, or like that. So the image is always going to be somewhere along that line. The farther away you get, the smaller the image appears. The closer you get, the larger the image appears. In fact, if you were to place your object right here, well, the image would also be right there and be the same size. Okay? So, for a convex mirror, the image is always virtual. The image is always reduced. In fact, this one right here where it's right against the mirror, you can't actually get that because of the curvature. So that's not even a real option. So the image is always going to be reduced, and the image is always upright compared to the original object. No matter where the object is, as long as it's, observable, that's going to be the case. Now, what's an example of a mirror like this? Well, an example of a mirror like this is, the mirror that's on the side of your car. The mirror that's on the side of your car, remember what it says. It says objects in mirror are closer than they appear. That's because if I were to look into the mirror and see a car, let's say on my right-hand rear view mirror, rear side mirror, then the car appears smaller than what I think it should. That's why those warning signs are there, just to let you know that the objects in the mirror are going to be closer than they appear because of the reduced nature of the image that you see. They are smaller and therefore they seem farther away. Okay, now we've done ray tracing for all of these two reflective mirror cases, concave and convex. As you probably can guess, you can also do a little bit of math and figure all of this stuff out. All right, so let's define some mathematical terms here. Let's let f be the focal length, and that's the distance from the mirror to the focal point. So that can be positive or it can be negative. In fact, f, you've already seen, is going to be positive for concave, and it's going to be negative for convex. And then we know that we have r. R is the radius of curvature, and r, it turns out, is going to be always going to be positive. It's always a distance, so it's positive, even though the focal point itself is positive or negative. The center of curvature could also be positive or negative. But we're not going to worry about those for the most part. Let's define one other. Let's say distance, and let's symbolize object distance as d sub o. And d sub o, well, that can be positive or negative. It's going to be positive for a real object. That's an object that's in front of the mirror. Or it's going to be negative for a virtual object. That's one that's behind the mirror. Now you might say, well, when can you ever actually have a virtual object? If it's behind the mirror, it's not going to reflect. Well, if you have more than one mirror, it's possible for one mirror to form an image behind a second mirror, and then that image become the object for the second mirror. And in that case, it could be virtual. All right, let's also define d sub I. I don't know why I'm writing things 2 times here, but I'll keep doing it. D sub I, that's the image distance, and that's going to be positive for real images, and it's going to be negative for virtual images. All right, we'll also define M, that's magnification, and magnification has a sign associated with it. It'll be positive for let's call it non-inverted. That way we avoid the upright use of that term, and negative for inverted. And that's non-inverted and inverted compared to the original object. All right, so with these things defined then, we can talk about the mirror equation. And the mirror equation looks like this. 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. All right, that's one of the equations. That's a mirror equation. That's definitely one that you should know. Another one deals with magnification, and magnification, it's really defined this way. Image height divided by object height. So the magnification is the ratio of the image to the object. Now, if we can also define it this way. It is minus di over do. So that one right there is one you also should know. And you see the negative sign there goes with the positive negative nature of the right or upright or inverted, non-inverted. Okay, but magnification itself is just a comparison of sizes. So it's the ratio of the image size to the object size. And that makes sense. All right, let's work a problem. Let's say that we have a concave mirror and that we have an object that is located 27 centimeters in front of the mirror. So the distance to the object is going to be 27 centimeters. And we have the image for this one, and let's say the distance to the image is 65 centimeters behind the mirror. Okay, that means the distance to the image is going to end up being negative because it's behind the mirror. Now, you could solve this using ray tracing if you very carefully laid out a line and a graph and you very carefully measured distances here. You could solve this sort of thing using ray tracing. But the question is, what is the magnification and what is the focal length? All right, well, you can also use the mirror equation to get this. 1 over f plus is equal to 1 over d sub o plus 1 over d sub I. And we're after the focal length here. So this is going to be 1 over 27 centimeters plus 1 over negative 65 centimeters. And that's what 1 over f is. So use your calculator, solve for f. Let's see what I get. 46.2 centimeters for the focal length. And it's positive, so that would make sense because it's a concave mirror. All right, now let's look at magnification. Magnification equation looks like m is equal to minus di over do. So that's going to be minus, let's see, di is minus 65 centimeters divided by do 27 centimeters. You'll notice the centimeters cancel, so that means magnification has no unit associated with it. And this turns out to be minus a negative, so it's going to end up being a positive value, which means that the image is going to be non-inverted. That's what we would expect if the if the object is located inside of the focal length. That's exactly what you should expect. That's this case here, where the object is inside the focal length here. So we expect the image to be virtual. We also expect it to be enlarged here. All right, let's see if that works out. 65 over 27 is going to be a number bigger than 1. And it turns out that that is 2.4. So the magnification is 2.4. That means that ever how tall that little arrow happens to be, the image is going to be 2.4 times larger. Okay, and the positive sign here indicates that it's not inverted. So if the object were 1 centimeter in height, the image would be 2.4 centimeters in height. Okay, we'll pause right here for reflection, and we'll pick up refraction in a future video.